So we're going to start talking about separable differential equations. And so really we're just talking about derivatives, but breaking it down into pieces. So when we think about our typical derivative notation, which you see right here, dy dx, we're thinking about that as being a function of x and y. So it has both variables. And the solution of that is y, some function that is in terms of x. So this is defined on an interval of x values such that the derivative of y being that function of x is x, y of x. When y, the function of x, and its derivative y prime of x, are substituted into the differential equation, the resulting equation is true for all x that exist on that solution interval. The general solution contains all possible solutions, and it always contains an arbitrary constant. Equations are separable if that function f can be expressed as a product of both a function of x and a function of y. This leads us to a standard differential equation form, which I will derive here. So if we think of dy dx being equal to g, a function of x, times h, a function of y, we can say that dy dx is equal to g of x times h of y, like this. I can divide on both sides by h of y and multiply by the d of x, which would give me dy divided by h of y equals g of x times d of x. And if I spread this out and integrate it a little bit, I can integrate on both sides, which is a legal operation. The integral of 1 over the function h in terms of y times d of y is going to equal the integral of g of x dx. And so now that we have it in this form, we can run through the process, completing the integration on both sides, and we will have a solution which is y implicitly defined as a function in terms of x. So for our first example in this section, we're going to solve a differential equation. In this case, we have dy dx is equal to the product of two functions, the first being 1 plus y, and the second one being e to the x. And then we have a restriction that we create and say that y is greater than -1. So solving this, what we can think about is that since y plus 1 will never equal 0 because of this restriction, we can solve by separation of variables. So I'm going to multiply by dx on both sides. I'm going to end up with dy equals 1 plus y e to the x dx. And I can divide by that 1 plus y on the left side of my equation. So now I have dy over 1 plus y equals e to the x dx. And this is very similar to what I derived on the first page. So working to simplify this, we can then say, well, I should correct myself there. Simplifying this, we're going to integrate on both sides, and by integrating on both sides, I'll end up with the natural log of 1 plus y And then the integral of e to the x is e to the x, and we put our arbitrary constant on there. So now what we have y is an implicit function in terms of x. So continuing to think about solving this, and so then this is our answer here. I started to go to another page in my notes. Apologize for that. It's my first video. But this is our function. This is a function of y implicitly defined in terms of x. We've got x's and y's on both sides of the equation. So I'm going to do one more example for you guys on the next sheet. All right, guys, we're going to do one more example. We're going to solve another separable differential equation. So in this case, what we're going to do is I'm going to multiply by dx, divide by that y squared plus 1, get things on other sides of the equation. So when I do that, I'm going to end up with y over y squared plus 1 dy equals x divided by x plus 1 dx. So after this step, we've multiplied and divided on both sides of the equation. We can integrate each side. So I've got the integral of y over y squared plus 1 dy equals the integral of x over x plus 1 dx. So continuing this, on this side, when we integrate on the left, we have to do a u substitution in order to do that. And during this u substitution, we would say u is y squared plus 1, so that means du is 2y dy, or 1/2 du equals y dy. On the right side, what we're going to do is we're going to be doing a division of x by x plus 1. So the integration on the left is going to be 1/2 the integral of 1 over u du, which will integrate and we'll end up with a natural log. And on the right side, what we'll end up integrating is the integral of 1 minus 1 over x plus 1 dx. And in doing that, on the left, we end up with 1/2 the natural log of 1 plus y squared. And on the right, the integral of 1 is x. And the integral of 1 over x is going to give us negative ln, the absolute value of x plus 1. And then we always end with our arbitrary constant plus c. And so this would be how we have solved our separable differential equation. And thanks for hanging in there with me, because that was my first video in a long time.